some reason the chat window and the sharing of the video don't seem to work simultaneously. So if you have a chat with him, then it makes life easier. So just let him know that he should communicate with you if he has questions.
Okay.
But ask him if he can see what's going on and hear what's going on. I really think we need a better system in the future.
Okay, should I start?
Give a few minutes.
Oh, okay, yeah.
Sorry? No, did you hook up another mic as well?
Oh,
Or does it work anyway?
Yeah.
Oh, wow. Oh, you have multiple mics. Well, that's a big font. I'm a bit scared now.
Okay, let me just do a quick walk around and be back.
We need to change the on-by power. Yeah. So we have what's in the morning. In the morning, in the afternoon, right? Yeah. Actually, no, last time I could do this. Sorry, from the last one. So we should try to do that in the discussion.
Sanjay, we can remind people tomorrow morning at 9:30.
Yes. Okay.
We haven't changed that on the
Back to that. Okay. All right, let's get started. Before we start today, I just want to remind everybody that tomorrow's talk will start at 9:30. And today we have Masaru Shibata telling us about binary neutron star mergers, both the gravitational waves and the electromagnetic counterparts.
thank you. So first of all, I'd like to thank organizers for giving me an opportunity to give a talk here. So today, I'd like to talk about the latest our progress in the merger of binary neutron star simulation, in particular focusing on the gravitational waves and the electromagnetic counterparts. This is the content of this talk. So after a brief introduction, so I would like to summarize the current understanding of binary neutron star mergers, which is obtained by numerical-relativity. And then so I'll talk on the gravitational waves and the equation states. So gravitational waves from the binary neutron stars, and that reflects the equation state. And then so in the section 4 and 5, so I'll talk on the mass ejection and related topics. Okay, so first of all, let me remind you that probably so all of you are familiar with these topics, but I'll repeat why binary neutron stars are important. So I think that there are at least 5 motivations so for studying the binary neutron star merger. One is that it is a most promising source of the gravitational waves for advanced LIGO and BARGO and so on, and Kagura, so I should say Kagura. And second motivation comes from that binary neutron star merger is in a sense a huge collider of neutron star matter. So this means that this is an invariable laboratory for studying the high density nuclear matter. So this means that it's a deserve detailed study from viewpoint of nuclear physics. And also, so it's so it has been proposed that binary neutron star merger is one of the most promising origins of short GRB. So we have to explore that what happens to binary neutron star merger, in particular focusing on the thermal properties of the merger remnant. And so recently, so it is getting popular that so merger remnants and not merger remnants, so mass ejection could occur during the binary neutron star merger, and such a ejecta could shine as an electromagnetic counterpart of gravitational waves. So we also needed to study such topics. And finally, so also it is related to the mass ejection. So ejecta is usually neutron rich, and so this means that it could be a source for production of heavy elements. So R process heavy elements. So this is also a new topic in numerical-relativity. So today, so I focus on these topics. So okay, so before going ahead, so I'd like to tell you that the current understanding of a binary neutron star merger. So anyway, so for scientific simulation and the scientific study, so we need a realistic initial condition. And so first of all, I would like to talk about what is a realistic initial condition, so which can be guessed from the observation. This is parameters of compact binary neutron star mergers in our galaxy. So this is these data. So this anyway, so we know at least there are 6 binary neutron stars in our galaxies, and these data are taken from this one, this one. And so this shows that binary parameters are fairly universal. So for example, so let's see the mass. So this is the mass of 2 neutron stars. This is the first-born neutron star, and this is the second-born neutron star mass. And this shows that the mass is in a range between 1.23 and 1.44. So this is so this means that the mass is in a very narrow range, and with a typical neutron star mass in binary is about 1.35, like this. And also, rotation period is fairly also uniform. So typically, so this is for these 5. So we believe that this is a rotation period pulsar, and we believe that these pulsars are first-born neutron star. And for first-born neutron stars, typical rotation period is several 10 milliseconds. So not very fast. So usually, so if neutron star is rapidly rotating, period should be about 1 millisecond or 2 milliseconds or something like that. So compared with this rapid rotation, this value is much larger, and so this means that spin is not very important for this system. And this is a magnitude of the strength of the magnetic field determined from the orbital rotation period and period derivative. And this also has a fairly uniform value. So typical value is 10 to 10 Gauss. And only for this, so we believe that a second-born neutron star is observed. And in this case, the values are completely different from this. So for this case, so magnetic field strength is very typical, so 10 to 12 Gauss. And also the spin period is more than 100 milliseconds. So, and also for this system, so for double pulsar system, the second pulsar is observed, and magnetic field strength is very similar, and rotation period is very long. So this shows that binary neutron star has a fairly uniform, so universal parameters. So for example, for considering binary neutron star, we should employ the mass in a very small range like this. And also for as for the spin, so spin should be not very large, so maybe negligible. So negligible means that compared with the orbital period just before the merger, this is more than 10 times larger. So, however, most crucial uncertainty comes from the equation of state. This is the neutron star mass as a function of the neutron star radius taken from this paper. And so each curve shows that the relation of mass and radius for a given equation of state. And there are many variations. So, however, so recent discoveries of 2 solar mass neutron stars, this one and this one, significantly constrain the chosen equation of state. For example, G's should be rejected. But there are still many candidate equation of state. And also, so Jim strongly constrained, so wrote a very interesting paper, so which constrains the equation of state. So constraint came from the Excel observation. But still, there are still fairly wide range. So this means that we have a huge possibility for a nuclear equation of state. So this means that on this study, for this study, so we have to employ the many equation of state. So I mean that only one simulation with only one equation state is not appropriate for this study. So we have to perform many simulations employing the many equation states, many possible equation states, and something like this. So this is a summary for the initial condition to be employed. So mass is likely to be in the range between this one, so in a fairly small range. And the spin is likely to be negligible or small. And the B field is something like this. But we don't know the equation of state, so this means that we have to employ a wide variety of possible equation of state. But except for this, so the problem is fairly well defined. So this is a good thing for binary neutron star merger. So only uncertainties, almost only uncertainties come from this one.
Masaru,
Yeah.
I can't see Chris because he would be the right person to ask this question, but the mass distribution that we observe is clearly very narrow between 1 to 1.5.
Yeah.
But is this what we would expect from population synthesis? In other words, are we not blinding ourselves because of some selection effect that prevents us from seeing heavier neutron stars?
Yeah.
What do we know about this? Maybe also Jim might have an opinion.
Chris? Chris is not here.
Chris is the one
Yeah.
population.
But so this distribution is fairly consistent with the population synthesis study. So anyway, so in the population synthesis study, so after the first born, so after the first neutron star is born, in the subsequent stage, so mass accretion occurs and the common envelope phase is produced, and then so two objects approach each other. Then so supernova explosion occurs. So if the kick velocity of supernova explosion, usually so we expect that the high kick velocity about 300 km per second or 4 km per second. So this means that if the orbital separation is large, so this system will be disrupted. So this means that we have to have a very close orbit just before the second explosion, or huge amount of mass stripping is necessary. So for this case, so second supernova could be a oxygen, neon, magnesium, electron capture supernova. Then so kick velocity could be very small. So anyway, so for such case, so for example, for the Onemag electron capture case, so mass should be very small. For example, so someone speculated that this system, this neutron star, may be a result of the Onemag supernovae. And also, because so low magnetic field supports this hypothesis because due to the mass accretion, usually magnetic field decrease, and this suggests that such a phase exists for
What I
half
was wondering is during the common envelope phase, the first born neutron star might accrete quite some matter. And so might go above 1.4.
Yeah. So my guess is that if quite huge amount of matter is accreted, then so common envelope phase continue very long for a very long time. Then so two objects could merge, according to the population synthesis study. And this shows that the accretion time scale is not very long. So if it's very long, so it could be a millisecond, but it is about a 10th millisecond. So it's very interesting. Also magnetic field strength is not very small. So for example, for millisecond pulse, magnetic field strength is 10 to 8 or 10 to 9 Gauss, but it is larger. So it's very interesting. So it's mystery. So it's a special class. Yeah. But I don't know. I don't know exactly. So
yeah, the only comment I would make is that it seems that it's fairly consistent with population synthesis models according to Chris's recent papers. I should mention for object number 5, the masses were recently remeasured. So the first one is 3/100ths of a solar mass larger, and the second one is 3/100ths of a solar mass smaller.
This one?
No,
this
number
one?
5. This one. Yeah.
Number 5?
Yeah.
Oh, recent paper.
Yeah, very recent.
Yeah. Okay, so anyway, so this is a summary for the initial condition to be employed. And so initial condition is fairly well defined for this problem. This is a nice thing. So from now, so let me show you at the latest understanding of binary neutron star merger. And so before telling about this topic, so I should say that there are at least two expected fates for binary neutron star merger, broadly speaking. So one is that black hole is promptly formed after the merger. So the other is that the massive neutron star is formed after the merger, at least transiently. And the fate could depend strongly on the total mass and the equation of state employed. However, so latest observation and latest initial condition to be employed constrain the final fate very strongly. So, and numerical-relativity study shows that fate 2 is most probable. So massive neutron star is so likely to be formed, at least transiently. Okay, let me show you animation. So in the following, so I'll show 4 animations at the same time. And for all of them, so mass of 2 neutron stars is 1.35 and 1.35, but the equation of state are different. So APR4 and RF2 and H4 and MS1 and so on and so on. For this equation of state, so radius of this mass neutron star is different. For this case, so mass is so radius is rather small, but for this case, radius is rather large. But so independent, irrespective of the these conditions, final fates, not final fates. So remnant after the merger is a hypermassive neutron star. So this is a density in the equatorial plane, and then after the inspiral phase, so 2 neutron star merge, and then it doesn't collapse the black hole. So massive neutron star is formed, and also massive neutron star is formed, and also massive neutron star is formed. Of course, after this phase, so for some models, so black hole may be formed, but at least about 10 milliseconds, for 10 milliseconds, so hypermassive neutron star is arrived. So this is a conclusion from a recent study. So massive neutron stars are remnant irrespective of equation of state for canonical mass. Of course, if the mass is much larger than this value, so black hole may be formed promptly. But for this typical value, hypermassive neutron star is formed. And hypermassive neutron star evolve as a result of the angular momentum redistribution. So this is animation. So animation is a meridian plane, and this is a hypermassive neutron star. And during the evolution, angular momentum is transported, and eventually black hole is formed. And due to the angular momentum transport, so disk become fairly large. So for example, for this example, mass of a disk is about 0.05 solar mass, fairly large. And also we found that the typical black hole spin in this scenario is at about 0.6, 0.7, not very large, but not very small. So this is a very typical value, so irrespective of the equation of state. Okay, so
approximately what's the temperature at the inner edge of the disk?
Oh, in this case, about 10 MeV, 10 MeV or maybe more, but roughly 10 MeV. Okay, so this is our last. Yeah.
Can I ask you something? In the animation you showed before,
Yeah.
is there a reason why there is no symmetry across the?
Oh, so this is asymmetry due to the visualization. So in this animation, so binary neutron star move like this. So we also plot only this one. So front one. So we have no. Which asymmetry? Asymmetry here? Yeah. So asymmetry. So of course there are very small asymmetry like this, but except for this, so this is simply a visualization asymmetry. No symmetry, yeah. Essentially no symmetry. Okay, so this is a latest scenario for the last 15 minutes of binary neutron star. So binary neutron star evolved due to the gravitational wave emission and eventually merge. Then anyway, for hypermassive neutron star is likely to be formed for a canonical mass of binary neutron star. Then this hypermassive neutron star could collapse to a black hole surrounded by an accretion torus due to some angular momentum transport. Here, so angular momentum transport is maybe driven by a torque, hydrodynamical torque or a magnetic field. But anyway, so by a angular momentum transport, black hole surrounded by a disk is formed. Okay, so next, I'd like to talk about the gravitational waves. This is a typical scenario for a binary neutron star merger, so as I explained in a previous view graph. And this is a typical corresponding gravitational wave form. And in the very early in spiral phase, gravitational wave form is a chirp signal. So it is characterized by a mass and spin of 2 neutron stars, and spin probably is almost negligible. So this waveform is characterized by 2 mass. But near in the cross orbit means that separation is about less than 5 neutron star radius. For such phase, tidal deformation effect play an important role. And then gravitation wave is slightly modified from the point particle one. And eventually, binary merge, and then we have a merger waveform. So during the evolution of a massive neutron star, hypermassive neutron star, because a hypermassive neutron star is not axisymmetric, but non-axisymmetric gravitational waves, something like this, are emitted. And eventually black hole is formed, and then you will see the quasi-normal model ringing. And there are 2 interesting phases for gravitational waves associated with the equation of state. So these are 2 phases. One is the in spiral phase. So rate is in spiral phase. So as I said in the previous view graph, so gravitational waves in the rate in spiral phase could be modified by the tidal effect. And strength of tidal effect depends on the radius of neutron star, and as a result, this phase depends on the equation of state. And for this phase, frequency of gravitational wave is about 100 Hertz to 1 kilohertz. The other interesting phase is that merger phase. So as I said, after the merger, massive neutron star is usually formed, and quasi-periodic gravitational waves is emitted. And for this phase, frequency is about 2 to 4 kilohertz. And this frequency depends strongly on the equation of state. And both waveforms could be used for constraining the equation of state of neutron star.
I have a question.
Yeah.
So in the post-Newtonian part,
Yeah.
A binary black hole with the same mass, the same spins, and a neutron star, the waveform will look basically the same. Is there a region in which the binary black hole waveform and the neutron star waveform still match but are beyond post-Newtonian before you get the effects of tidal deformation and so on?
So I have never tried to analyze, but so of course around here, so 2 waveforms match.
But is there a region in which post-Newtonian is already failing?
Yeah.
But it's still the BBH and the double neutron star waveforms kind of match before then they depart because of tidal couplings and so on.
Yeah, probably no one knows.
Okay.
No one knows. It's interesting to explore. Yeah. So probably Caltech. So in Caltech, Roland Haas is performing a very long simulation and comparing with his binary neutron star gravitational waves with the binary black holes. Maybe he knows the answer, but I don't know. Yeah. Okay, so let me briefly talk why the this phase. So relative spiral phase reflects the equation of state. So I think that this is originally pointed out by Don Lai and Stu Shapiro many years ago. So for cross-binary system, anyway, so due to the companion star is deformed like this. And then so Newtonian-like potential is modified like this. So this is a usual point mass Newtonian potential. And but in the presence of the tidal deformation, this type of R6 term appear. So this is very small for distant orbit, but for cross orbit, it could be very important because C is very large in this case. Here, C is roughly proportional to the mass to R square, R fifth. So this means that compared with this term, so magnitude of this term is a large R to small R fifth term. So this means that for cross orbit like this, so this coefficient, this term could be fairly large, comparable, not comparable, but could be 10% of the primary term. So as a result, orbital motion is modified and also gravitational wave forms are modified. So this is a very simple explanation why the relative spiral phase here is modified by the tidal effect. This is some example how the tidal effect is important. In this example, so we calculate the orbital motion by the effect of one body formulation. For this case, so 1.35 solar mass, and EOS is rather stiff, so with a radius is 14.5 kilometer. And the red line shows the result in the absence of the tidal effect, and green line shows in the presence of the tidal effect. So this shows that it disappears. So this shows that in the early phase, two orbits almost agree, but near the merger, two orbits become getting deviating. And also due to the tidal effect, so approaching velocity is accelerated, so green one. So and the merger time is become earlier. And also this effect is reflected in the gravitational wave form. So this is the this is another example of a gravitational wave form. In this example, so I use Taylor T4 plus tidal deformation effect, and black line, black curve shows a result of gravitational wave form by usual Taylor T4 formulation, so point particle approximation. And red, green, and blue curves shows a case or in the presence of the tidal effects. And this shows that this is for this case radius is about 11 kilometer. For this case radius is about 13.5 kilometer, and in this case radius is 14.5 kilometer. So this means that for this case, so tidal effect should be strongest. And this is well reflected in the this figure. So for this, so for example, compared with the blue and black, so you see that for blue case, so merger occurs much earlier than the black case. So this is due to the tidal effect. So tidal effect accelerates merger. So and so this anyway, this is a very interesting, and if we could detect a gravitational wave, something like this, so we may constrain the equation of state. So motivated by this idea, so there are many works in the past 3 years, and what is it seems to me what is most interesting is that analysis by Damo and Naga and 2 years ago, they performed some analysis in terms of the effective one-body formulation, and they suggested that for this mass binary, or less massive binary, EOS could be constrained for signal-to-noise ratio larger than 16 events. However, so Wade and his collaborator show that systematic error in the template will give serious damage for this analysis. So So then, so we have questions that can EOB provide accurate templates or not? So if template is not accurate enough, so we cannot say anything about because of this paper. So in numerical relativity, what is necessary is that how good the EOB, or we could construct the better formulation for accurate template. And motivated by this subject, so recently Bernizzi and Hotokezaka et al. Showed that performed a fairly long-term simulation. Long-term means that about 10 orbit simulations, and compared the waveform with the EOB waveform. And they showed that EOB is acceptable, at least for the about 1 or 2 orbit before the merger. However, their simulation are not very long, so 10 orbit is not very long. And also, the other problem is that the initial condition is not very good. So I mean that at that time, so we use a quasi-equilibrium state as an initial condition. But such an initial condition has a non-negligible eccentricity. So non-negligible eccentricity means that the eccentricity is about 0.02 or 0.3, 0.02 or 0.03. So such a eccentricity is very large in this study. So we have to perform a more sophisticated simulation on this issue. And there are several efforts in this area, in this field. For example, so QTOC here, QTOC here, there, perform so studies eccentric reaction initial data. So anyway, so he improves the initial condition, reducing eccentricity. And this is his result, and this is a waveform. Anyway, so in this waveform, so eccentricity is now about less than 10 to the minus 3. So for example, this is amplitude as a function of a time. So in the previous code, so amplitude behave like this. So this I forget the name. Anyway, so this curve. But magenta curve. But so anyway, so he performs the iteration to reduce the eccentricity, and in the third iteration, so eccentricity becomes very small, and curve. So also there are small modulation. A curve becomes fairly smooth. So for such curve, so eccentricity is about 10 to the minus 3. Also, so Caltech team, so Roland Haas, is also working in a very long-term simulation.
Masaru?
Yeah.
What are those little oscillations that you see in the red? Are they modes of
So,
oscillation of the star? Or?
so he suspected that this is due to the reflection of at the refinement boundary, but I'm not sure.
We confirmed that that small modulation is not associated with stellar oscillations because I performed the Fourier expansion of density profile. So that is not due to stellar oscillation.
Okay.
And also, we recently performed a 15-orbit simulation. It's still preliminary. So this is a 15-orbit simulations. And so it seems, for me, it's very impressive. So because in our previous simulations, circular orbit is not very circular orbit. But now, so it is very circular orbit. It looks very circular orbit. And this is so wild scalar as a function of retarded time. So and this is a numerical result for a particular resolution, and the black curve shows a result by effective one body calculation, and so fortunately, so it works much well. So in the early inspiral stage, the problem is anyway is in the final few orbits, and for this it's not very still clear. Anyway, so in the first in the early inspiral phase, so two curve much well. So you can see the black curve. So anyway, so in the early about 1, 2, 3, 4, 5, 6, 7, 8. So for early 7 orbits, two curves match very well. But in the rate phase, so two curve slightly deviates. So anyway, so we have to be careful. So in the early phase it works well, but in the rate phase it does not much well. So we need a very careful resolution study. This is a frequency, so angular frequency in unit over m. M is a total mass. Angular frequency as a function of retarded time, and we plotted the three curves with different grid resolution, and for for poorer grid resolution, so merger time is earlier. This is due to the numerical dissipation. But with improving the grid resolution, merger time increase. And we checked that this is about a fourth order convergent. And by extrapolating this result, assuming the fourth order convergence, so we have this orange line. So this shows that in the rate phase, so two curves slightly disagree. So anyway, so from now, so we are going to perform a very careful extrapolation, and then we will compare the extrapolated result with a EOB curve or Taylor T4 curve. Also, this is amplitude, while scalar amplitude as a function of the retarded time. So as I said in the previous slide, so for poorer grid resolution, merger time is earlier, but with improving the grid resolution, merger time become approach to a realistic value, and this orange line is extrapolated value. And in the early phase, two curves match very well, but in the final phase, two curves don't match well. So anyway, so this is an issue to be explored in the future.
But isn't this consistent with your expectations? I mean, you do have some extra dissipation here, right? Relative to EOP simulations.
I don't understand what you mean.
No? Okay, sorry. Never
The
mind.
orange curve, I don't know whether you can see from the orange curve which is extrapolated,
Yeah.
is right on top of EOP, almost
Okay.
until that.
Yeah.
Okay.
Just last
But,
2
so
3 minutes, and this is very interesting. Incidentally, which is the EOB model? Do you remember the details of the EOB?
Oh, so it's original EOB plus 1 PN tidal effect.
So has it been tuned to then
Yeah.
some binary black hole simulation?
Yeah, so yes, so tuned to binary black hole, so up to the
How many orbits? and
5 p.m. 1 p.m. time, probably 5 p.m. time. So A4, A5, A6, yeah.
Oh, A4.
And plus tidal, 1 p.m. tidal time, yeah.
was there the extrapolated run about 50 milliseconds seems to give you a smaller frequency,
Yeah,
and then later on seems to be
a smaller amplitude.
sorry,
Maybe,
Yeah,
yeah,
frequency and-
yeah, slightly smaller frequency, yeah. So maybe so we should be very careful in extrapolation. Extrapolation may be wrong, but we haven't done anything. So from now, so
And you say you have fourth order up
Yeah.
until when?
until here, until in spiral phase. This is very rough order. So I'm not sure. Maybe 3.8 or 4.2 or any. So this is about fourth order. So
What methods are you using?
Oh, so I only computed. I only checked that merger time converge at fourth order.
Your numerical methods are of what order?
The fourth order.
Fourth order.
Fourth order. Now it's not BSSN. It's based on the G4C formulation. It is a key. In the BSSN, so order become 1.8 or something like that. But in G4C, it become about fourth order. Yeah.
Sure.
Yeah.
One thing about the extrapolation, the difference between the green and the red seems almost the same as the red and the extrapolated, which,
This one.
yeah, those two
Oh,
differences.
yeah. This is reasonable. So in the fourth order convergence, this size is comparable.
Well, but I'd expect it to get smaller.
No. So this is fairly large, still large. We need a better resolution. Then so expect it to be very small. Yeah. This is, yeah, it's very simple, assuming the fourth order convergence. So this size, yeah.
Well, right, but the difference between the blue and the green is big,
Yeah.
and green and red is small, so it's converging. But then if you're going to extrapolate to even higher,
Yeah.
it seems like the differences would continue to get smaller.
No. So this is correct. So no. Yeah. Yeah, fourth order is not very good. So if we have an eighth order or 10th order, so it could be very small. But fourth order is not very good. So
is going to higher resolutions just limited by computation, or is there some other
computation?
Oh, okay.
Computation. Yeah. Yeah. We would like to finish one model computation within 2 or 3 months. So this limits resolution. So I also, so I should say this one, but also so in the merger phase, so equation states, information of equation state is well reflected. This is the gravitational waves from the massive neutron stars. These are massive neutron stars with the same mass, but with a different equation state, APR4 and ALF2 and H4 and MS1. And this shows that waveforms are, so wave shapes are fairly universal, but frequency, typical frequency is highly different. For this relatively soft equation state, frequency becomes very high, more than 3 kilohertz, but for a very stiff equation state, frequency becomes 2 kilohertz. So this shows that if this frequency, these gravitational waves are detected and the frequency is determined, so we may be constrained the equation state. I think that this topic was also discussed last week, right? So I'll skip this one. Okay, so no. So I'd like to talk about mass ejection and electromagnetic counterparts. So first of all, so let me summarize that. I focus on the so-called dynamical mass ejection, not disk wind ejection or neutron wind ejection. So I only focus on the dynamical mass ejection. And for dynamical mass ejection, there are at least 2 effects which drives the material. One is that strong shock. So at the merger, shock is formed. Then so shocked material has a huge thermal energy, and then so it explodes. So the mechanism is very similar to a supernovae. In the supernovae, so we have a shock, and a huge amount of the thermal energy is generated, and matter is ejected. The other mechanism is tidal torque. So I mean that during the merged object has a non-axisymmetric structure, and then so hydrodynamical torque works very efficiently. Then so torque expels the matter in the outer region, and then some materials ejected. So we have 2 mechanisms. This is the key in this talk. Okay, so let me show you such a mechanism. So in this example, so I use this EOS, relatively soft equation of state, and the mass is 1.2, 1.5. And this is a density contour in the equatorial plane. And this is a smaller region, and this is a wider region. For this, so 300 cube, and this is about 2,000 kilometers square. Okay, anyway, so at the merger, shock is formed, and also tidal effect plays an important role. Then tidal torque effect play a role for ejecting matter. And in this example, head speed here is very high, so about 0.8 c. And also total ejector mass is, in this example, is 1% of the solar mass. And the average ejector velocity is about 20% of the speed of light. This is one effect. So by the tidal torque, so matter is ejected along the equatorial plane. On the other hand, we also have the shock heating effect. This is animation in the meridional plane, xg plane. And this is a smaller view, and this is a wider view. So after merger, shock is formed. And by the tidal effects, mass is ejected along the equatorial plane, but by the shock heating also, mass is ejected towards the rotational plane. This is a wider view. So and as a result, ejecta become fairly spherical, so quasi-spherical. So this shows that shock heating effect play an important role. So only with the tidal torque effects, mass is ejected along the equatorial plane, but with the shock heating, ejecta become quite spherical.
I mean, the density distribution though is not spherical.
No.
I mean, the front is spherical, but the distribution.
But what I mean is that in the absence of shock heating, almost no matter along here. But in this case, matter, appreciable amount of matter ejected along the rotational plane.
But how about emission? When you think about not dense, let's say, I think the question was the density is different in equatorial plane and horizontal plane.
Yeah.
I mean, what's the emission will look like? Would it be isotropic or not isotropic?
Almost isotropic, because it's almost, so what to say, even if we observe from here or from here, so we observe whole the sphere, right? So then, so.
Well, it will be cooling differently, I would think.
Yeah, so we naively expected something happens, but so my colleague performed a radiation transfer calculation for this eject, and he showed that so directional effect is very small.
You know, I talked to Los Alamos people and Dan Kaysen as well, and they think the emission will be non-isotropic.
Oh, so maybe so the problem is the degree of how large degree. So.
Of course.
Yeah. Of course, it's anisotropic, but not very anisotropic. So I mean, yeah. Oh, in this case. Okay, so anyway, so there are two components. This is a density conserved ejector, and we have two components. One is a tidally induced component. So it expands along the equatorial plane, and because the tidal torque play an important role in this case. So in this case, shock heating doesn't play an important role. So temperature is not very high for this case. By contrast, we also have a shock heated component near the vertical axis. And in this case, matter is ejected by the shock. So as a result, temperature is high. So anyway, so we have two components. But also the picture depends strongly on the equation of state. This is a summary of the ejecta mass as a function of the radius of neutron star. So for this case, neutron star equation of state is fairly soft, but for this case, equation of state is stiff. And this shows that for a small radius neutron star, ejecta mass become typically 0.01 solar mass. And so here, so I'm showing that the result for equal mass case by red and unequal mass case triangle. And also we have many other unequal mass result. But for this case, so total ejecta mass is only weakly dependent on the mass ratio. So this means that shock heating play an important role, because in this case, radius is very small, so shock heating effect is very strong at the margin. By contrast, for larger radius neutron star, if we consider the equal mass case, mass of ejecta is very small, about 10, by a factor of 10 smaller than the compact case. But for unequal mass case, in this case, tidal effect play an important role, and mass increase like this, but still smaller than these cases. So this is one interesting finding. So, but anyway, so for this case, shock heating play an important role. But for this case, for mass ejection, tidal effect is key.
So for soft equations of state, state, you're getting relatively more mass ejection.
Yeah.
If I were to contrast this with, say, neutron star black hole merger,
Yeah.
so different. I think
Yeah.
Toyota have done simulations where I thought for
Not
state
exactly.
equation of state you get more mass ejection. So is the difference occurring mainly because of soft?
So I guess
Yeah,
what
I
tidal
see.
effects
Yeah, this
dominate
one.
or shock heating dominate.
Exactly. So that's interesting.
This one, this one. This is a binary neutron star, and this is a black neutron star. Yeah. In this case, tidal effect is only a play a role. Yeah.
So have anybody looked at post-processing core? I mean, so the shock ejecta is hot.
Yeah.
Presumably its nucleosynthesis
Yeah.
will be slightly different from
Yeah.
the cold ejecta.
Yeah.
And has anybody looked at whether this is observationally discernible in the most optimistic scenario?
So we are just doing. So I'll talk later. Yeah. Anyway, so mass is ejected, and there are two mechanisms. Two possibilities that ejecta could generate a electromagnetic signal. One possibility is the so-called popular Kilonova macronova scenario, which is based on the radioactively powered emission. And the other is afterglow type radio flare scenario. In this case, ejecta sweeps the interstellar matter, and then mass of interstellar matter become large enough, a shock is formed, then synchrotron type radiation occurs. But for this scenario, electromagnetic counterpart will be seen after the about 10 years or something like that. But for this case, electromagnetic counterpart will be observed within about 10 days. So today, I focus on this scenario. Okay, so anyway, let me remind you that what is the detail of a scenario. Scenario is based on the R process nucleosynthesis. This is elements, so proton number and neutron number, and the black square shows that stable nuclei, and in the R process nucleosynthesis, heavy nuclei is produced along this line due to the neutron capture. So this occurs when neutron capture timescale is much smaller than the beta decay timescale. And the other important thing is that in this R process production, we usually have 3 peaks, which are associated with a magic number of neutron here and here and here. But anyway, by the R process nucleosynthesis, a bunch of unstable heavy nuclei are produced. So motivated by this fact, Li and Paczyski considered the original Kilonova macronova scenario, and anyway, neutron-rich ejecta could be ejected. Material could be ejected. Then it could produce a heavy nuclei through the R process nucleosynthesis, which was originally proposed by Jim 40 years ago, many years ago, 40 years ago. And then unstable nuclei. Anyway, by this process, a bunch of unstable nuclei are produced, but then it decay by a beta decay or fission. Then by this decay, material is heated up. In the early phase of the after the mass ejection, expand freely. But also ejecta is highly dense, so this means that it is optically thick. So this means that emission cannot be escaped from the ejecta. But after the adiabatic expansion, ejecta density decreases, and at some point, diffusion time scale of photon become shorter than the expansion time scale, and then emission, efficient emission starts. According to the Li and Paczyski and the other guys, the other works, recent works, such ejecta could shine in the UV to infrared band. this is a estimate by Li and Paczyski, and according to their estimate, maximum luminosity become about 10 to 41 electrons per second for a hypothetical mass of ejecta 10 to minus 2 solar mass. Ejecta velocity is 0.2 speed of light, and kappa is the opacity. Opacity is fairly large according to the discovery by the Keisen and Tanaka. And this is a convergence factor of the energy to ejector. And also, so typical duration or typical peak days of this maximum value is reached is about 10 days, about 5 days, for a given mass and velocity and kappa. So, but this is a very naive estimation, and then so last year, so Dan Keisen and Tanaka performed a detailed radiation transfer calculation for hypothetical heating rate via R plus nuclear decay and solar abundance of R process element. And this is some example by Masaru Tanaka. And anyway, so he performed a radiation transfer simulation for ejecta. So ejecta data is imported from numerical-relativity result by us. And this is a light curve of optical to near infrared band. And this shows that ejecta is likely to be shine in the near infrared band. So in the optical band, so peak luminosity is reached in early time, but in the near infrared band, so peak time is reached in 5 days or 10 days. So probably such ejecta could shine in the near infrared band.
So a word of warning here for maybe for audience. Those calculations by Tanaka talk use very few lines of those R process elements.
Yeah.
So you have to take this with a grain of salt, or just with
yeah.
You know, Dan Keisen did millions of lines per element, but few elements.
Yeah.
So you don't have a full calculation yet of that process.
No. Yeah, you're right. Yeah. So yeah, there are many sort of mysterious things. So for example, this one luminosity is slightly smaller than the other one. Well, this is very mysterious. So the reason is that only for this case, so some line opacity become very important.
Yeah,
but yes,
we don't have opacity.
Yeah. And maybe so this may be smaller if the sign element, other elements are yeah, you're right. But it's very detailed. It's very detailed. And okay, so according to their result, we know now that for sufficient mass ejection. So for example, here, so we have 3 curves. So 3 curves. This is a curve for 0.01 solar mass. This is a curve for 0.004 solar mass, and this is a curve for 0.007 solar mass. Anyway, so peak luminosity is primarily determined by the mass, total mass ejected. And if sufficient mass is at about 10 to minus 2 solar mass is ejected, electromagnetic signal could be observed by, for example, a 4 meter class telescope or space telescope for a duration about 10 days. And also signal is strong in near infrared band. And they published this paper in May last year, but in June last year, so such a candidate is observed. So I think they are very lucky. And so this is the very famous paper by Tambir. And this is excess of the near infrared band. And this point is fairly well explained by this scenario. For example, so we did a detailed analysis, changing the mass and so on. And so this is our latest result. So this is an observation by Tambir. And for explaining our conclusion is that for explaining this excess, mass of ejecta could be very high, at least 0.02 solar mass or higher. So as I said in the several previous view graphs, for ejecting such a high mass, small mass neutron star is necessary. Otherwise, so ejecta mass is much smaller. if, for example, the mass of radius of a neutron star is about 13 or 15 kilometer, mass could be at most 0.04 or something like that. So to explain this point by a binary neutron star merger, anyway, so equation states should be relatively soft. Small radius neutron star is necessary. Okay, so should I stop or should I continue?
I think you probably have 5 more minutes.
5 more minutes, okay. Maybe you are very interested in this talk, so
Let's another 10 more minutes.
10 more minutes. Okay, so finally, so I'd like to talk about our ongoing talk. So anyway, so for example, for this calculation, so we naively assume that ejector should have a solar abundance pattern, and also and also we assume that very naive temperature distribution and electron fraction distribution. But to plot this type of curve, we need a self-consistent simulation. So we are just starting such a simulation. So this is a topic. And anyway, so probably one of the most interesting goals in this field is that to explain that FAT produces this abundance pattern. This is a solar abundance pattern of the every elements, and these peaks are the so-called first peak, and second peaks are third peaks produced by our process nuclear synthesis. And so we'd like to explain this one. And also this is I should say that this is a new subject in numerical relativity. And at least there are 2 scenarios to produce these peaks. One is that supernovae. So after supernovae, so neutron driven window may be ejected, and such a ejecta could explain this abundance pattern. The other is binary neutron star mergers. After merger by binary neutron stars, neutron-rich ejecta could be ejected, and such ejecta may explain this abundance pattern. So before going ahead, so I like to tell you that the FAT is a key quantity. The key quantity in this problem is that one is temperature, and the other is more specifically electron fraction per barium is very important. So YE is that electron fraction in 1 barium. For example, for helium, this is 0.5, and for carbon and oxygen also 0.5. And for neutron stars, this could be 0.1 or less. But anyway, so for making this abundance pattern by our process nuclear synthesis, so neutron-rich atmosphere is necessary, circumstance is necessary. And recent work told us that if YE is relatively high, for example 0.4, in this case neutron, because neutron is not very rich, and for such case our process could occur, but third peak, this peak, is not reached. So this peak may be explained, but third peak, it's very difficult to explain third peak because of the neutron less rich nature. By contrast, so if ejecta is very neutron rich, say so like the neutron star component 0.1, this is the case when the in the case of the ejecta in the black hole neutron star binary. For such case, neutron star matter simply ejected from the system, and the ejecta could have this value. Or anyway, so tidal effect is dominant. If tidal effect is dominant, very neutron-rich ejecta is the case. For such case, second and third peak are explained, but it's not easy to explain first peak. This was shown by Janka and his collaborator, and also Stefan Roth's work. This is the result. This is mass number, and this is a mass fraction, and this is a third peak. and this is a second peak, and this is a first peak. So in this calculation, almost nothing is produced in the first peak, and and also second peak cannot be explained very well. But third peak is explained very well because of the neutron-rich nature. And on the other hand, so latest study by Wanajo and Sekiguchi shows that it could be possible even by a binary neutron star merger. So the fact is,
make a comment
Hi.
on the left figure.
Yeah.
This result is very dependent on the distribution of fission.
Oh yes,
products.
yes. I'm sorry. Yeah, yes. Yeah. So in this case, so the fusion is not taken into account here. And so please forget fusion now. So okay. So in this case, fact is different is that as follows. In this case, ejecta, so mass is mainly ejected by a tidal torque. Then so ejecta become neutron rich. But in this case, so not only the tidal torque, but also shock heating play an important role. And then so for such case, Y distribution change. For this case, Y distribution is very narrow, so near the 0.1 or 0.2 or something like that. But in this case, so not only the tidal component, but also the shock heating component. As a result, Y distribution become very wide. Okay, so anyway, so this is a very schematic picture. So tidal component move along the orbital plane. For such ejecta, Y is very small. But for a shock heated case, Y could be very high. So let me show you the why. Okay, so I'll skip. Yeah. So this is the anyway. So let me show you one particular. We performed many simulations changing the equation set, but let me show you one particular simulation with a relatively soft equation state. Yeah, for this case, by the way, this is the Newton emission. This is density in the equatorial plane and the xg plane. At the merger, shock is formed, and then some material is ejected. And in this case, shock heating effect is important because of the small radius. Then so ejecta become a fairly quasi-spherical. Anyway, so ejecta escape in a quasi. Pardon?
So you have a shock from
Yeah. Yeah.
The velocity associated to that is 0.8.
Maybe. Yeah, it's very high.
And does it settle to the same value, or is it lower afterwards? I mean, not the shock front, but the matter.
So average velocity is much smaller, 0.2, 0.3. Yeah. But only front is very high speed. And then so let me show you which is better. So electron fraction. This is the electron fraction. So initially we put some atmosphere with which Y is 0.5. But anyway, so after the merger, ejecta is emitted, but so it's not easy to see. So here, so neutron-rich matter is ejected, but near here, it is not very neutron-rich. So let me show you again. So no, this is not this one. Yeah, please focus on around here, around here. So in the first moment, neutron-rich matter is ejected, but then neutron richness becomes very small. So Y increase. So neutron-rich matter is ejected, but after that, neutron-less rich matter is ejected. So this is due to the shock heating effect. Yeah.
With neutrino cooling but no heating?
Yeah, I mean, so everything is included in this case. But in this case, shock heating play an important role.
So the shock heating makes weak interactions rapid enough so
Yeah,
that
yeah.
you can now have higher
Yeah,
YE.
yeah, yeah. And also, so I should answer your questions. And this point is by shock heating. But around here, so we have very proton-rich region. So this is due to the neutron heating. So in this simulation, we include the neutron heating. Yeah. So here, so you see that YE is very high, 0.5 or 0.04 or something like that. This is mainly due to the neutron heating. But in this case, unfortunately, after about 20 milliseconds, black hole is formed. Then so hypermassive neutron star disappear. Then so neutron cooling disappear. But if in the presence of the hypermassive neutron star, then so neutron cooling will work along here. Okay, so anyway, so this is some reason why the electron fraction changed by shock heating. This is a picture for the electron fraction per baryon for a relatively soft equation of state, and this is the so-called Shen equation of state. Shen equation of state is a relatively stiff equation of state, and for this case, you see that here is a very proton rich, but in this case, so color is like this. So this means that neutron rich. So the reason is that in this case, shock heating effect is very efficient. As a result, the temperature is very high. Then so electron positron pair can be efficiently formed. Then so because originally so atmosphere is the circumstance is a very proton rich, so produced positron is captured by a neutron to be a proton like this. So this by this process, YE increase, and as a result, for compact case, proton richness is increased. So as a result, distribution of the YE change significantly. This is a result for 3 equation state. This is a compact neutron star, so middle compactness, and this is a very less compact neutron star. And for a compact neutron star, YE distribution becomes something like this. This is a YE as a function of fraction mass. And for this case, YE, peak value of YE is fairly large. And for such case, it's possible to reproduce a solar abundance. But for relatively for stiff equation of state, because the temperature is low and YE positron production rate is not very high, then so YE has a peak YE has a very small value. For such case, so third peak. So first, it's not very easy to reproduce the abundance pattern because of the lack of the first peak. Okay, so anyway, so we only calculated the YE distribution from now, so we needed to do a more detailed nucleosynthesis work. And I think that Wanajo and Nishimura and Sekiguchi are working in these topics. Okay, so let me summarize. Gravitational waves from binary neutron star is a viable site for exploring equation state neutron star. And efforts in numerical relativity are ongoing. And also, what is interesting in mass ejection is that total ejecta mass and the properties, thermal property and microphysical property depend strongly on equation state. And anyway, so for electromagnetic counterparts, total mass of ejecta is we want a high total mass of ejecta, and for such high total mass of ejecta, so relatively small neutron star radius is favored. And also, relatively small radius neutron star is favored for explaining the solar abundance pattern. If we don't consider the fission, so if we consider fission, so something may change. But if we don't consider fission, so small radius neutron star is favored. Thank you.
We have about 10 minutes for questions and discussion.
So I have a question about that last part.
Yeah.
So you did the study for our process elements, and you're trying to fit those 3 peaks.
Mm-hmm.
Okay. You have really 3 ingredients to play with. You have different ratios of mergers of neutron stars and black hole and neutron stars.
Mhm.
Then you have you can put different mass of ejecta in tidal heating and in shock, and then you have distribution, like James said, of fission elements. I would think that you have so much freedom right now that you should be in principle able to fit the observations.
Mhm.
And once you fit them, since you have so much freedom, my question is, what you hoping to learn from that?
So my hope is that anyway, we have only one EOS. So anyway, so and the mass. So as I said, so you are not here. So that's just introduction. So, but this is your topics. Yeah. For black hole neutron star binary, you have a bunch of parameter space, and the abundance pattern could be very different, and so on and so on. So my guess is that by black hole neutron star binary, it's very difficult to explain the universal abundance pattern.
But you know, in the universe, we most likely have mixture of 2. So you have to play with the mixture. That gives you the generosity.
Mm-hmm.
Right away. So I'm trying to see, do you really hope to get equation of state if you don't really know that mixture up front?
So
you have enough degeneracies that I'm worried that you will fit the observations,
yeah,
and you still won't be able to constrain equation of state.
Yeah. So let me say one possibility. Yeah. This is so you are very familiar with this this table. So yeah. Anyway, so parameters of binary neutron stars are fairly universal. So for example, mass is very universal, and spin is also very universal, and so on and so on. Only unknown is equation of state. But if I show that for a particular equation of state with such a universality, so we can explain the solar abundance.
Well, what if somebody tells you that 80% of mergers are black hole neutron stars and not box?
80%.
Let's say.
Yeah.
We don't know. It's back agnostic.
Yeah.
So then your conclusion goes out of the
yeah, of course. Yeah. In such case, I'm not very. Yeah.
Show that this
So in this case, I lost the bet. So yeah.
We should all think about.
Yeah. Anyway, so. Yeah.
Well, but I know how I'm saying that.
No. It's possible. So I don't do any. But because I like this one, so only I like. So I never say something here.
Yeah. Do you have a question?
Yeah. Part of it could come from core-collapse supernova. I'm wondering if core-collapse supernova don't give neutron-rich ejecta, do they still produce the first peak of the R process, and could they just dump a lot of material in the first peak, or do they just not produce anything at all? Do you know?
Yeah. So you said that is it possible to explain by mixture of
the first peak from the
yeah.
I mean, you see, if the ejecta is relatively high YE, you
could be.
Mostly the first peak.
Yeah.
Is that what you would expect from for the core collapse ejecta, or is it even higher YE and producing nothing at all?
Yeah, could be. Yeah.
I think it's more complicated than that, because we see individual R process events very early in the galaxy from the old Gaussian halo stars. So we know at metallicity below -3 that events are going off. They're singular events that produce the entire R cross distribution that we see in the sun from barium all the way up to uranium. So that's a tremendously strong constraint. We actually know something about the time scale of those events as well, because we can look at the statistics of things like Europium. And it tells us that these events are occurring roughly once every 100 years. So they're definitely not neutron star merger rates. So I would actually argue that the thing that's most interesting to us that are trying to look at whether there's a hybrid scenario of some class of events that works in the early galaxy that probably is dependent on the fact that the metallicity is very low to produce an R process. It's much easier to produce an R process with low metallicity. But it's unlikely that those events are so robust that they can produce all the metals that exist in our galaxy. So a really interesting scenario is a special R process that turns on at a very early time,
Mhm.
and maybe evolves us up to about a metallicity of -2. And then the neutron stars mergers taking over at that point, producing the bulk of the metal.
Yeah.
So the two things we need to know really are, what is the binary merger rate as a function of time
Mhm.
in the galaxy? And then what is the total amount of kinetic energy, not just the mass, but the kinetic energy that's going out in the ejected material? Because that determines the mixing volume, which is the other
Yeah.
parameter
Yeah,
we need to
yeah,
know
yeah.
Whether we can do the evolution in a nice smooth way.
Yeah, yeah.
But just from
Thank
the
you.
theory, it's possible to produce so-called weak R processes.
Yeah.
So 9 solar mass star produce first peak. That was the
But that's
Yeah.
not enough to explain the observations at low metallicity. You also need a second and third peak for that.
yeah.
right.
But multiple source could be.
Yeah. Yeah, so I don't ask, I'm beginner, so there are many experts.
Yeah.
So, Chris, I actually asked you a question because you couldn't hear it. Can you go back to the distribution of masses and spins? So we have a certain distribution we observe, and population synthesis can reproduce that. But is there something more that we are just not seeing because of selection effect? So the real question is, can there be binaries where we have, I don't know, 1.8, 2 solar masses, neutron star in the binary?
So we do get the range of those masses for current models, but those are only that would be only, you know, those are masses, and those are kind of given merger times, or let's say delay times. We get, for some models, for most models, we get populations with a much shorter lived that you wouldn't actually see in the galaxy, but because they merge on such a short time scale. So then you can ask the question: is the mass distribution different? We don't find it really, but again, it's modeling. I would say that given all our unknowns in evolutionary predictions, I would see, I cannot exclude that there exists a population that you don't see in a galaxy but has a different mass distribution or spin distribution that you see in the table.
Mm.
I cannot exclude that.
Mm-hmm. Yeah.
Okay?
Yeah.
And I definitely would be afraid to consider just neutron stars alone. I would consider both black hole neutron stars since they behave very differently.
Yeah.
Together with neutron stars on top of supernovae, like all three of those things must contribute at some level.
Yeah.
And somebody asked about like what would be like how would the merger rate would look across the galaxy over a cosmic timescale. So you can play that game. Of course, it really goes back to how the star formation history looks like in the galaxy. And you have those three components: you have halo, disk, and bulge that have different, not only metallicity evolution but also star formation histories.
Mm-hmm.
So it changes, but at the first level you can assume it's kind of constant.
Yeah.
It's not really, but you can play. We don't know them really.
Yeah.
That's my worry. That we're trying to come up with, or you guys are trying to come up with some conclusions here, but I see so many ingredients coming in that we don't know.
Yeah, it's only for galaxy.
At least, it should be very careful discussion of all those uncertainties once you reach a given conclusion.
Yeah. Thank you. Yeah.
Any other questions?
So the Tanvir et al. Result cannot be reproduced by a black hole neutron star?
Oh yeah, but so they prefer to black hole neutron star binary. So for black hole neutron star binary, so ejecta mass could be even higher. For example, 0.1
So
or.
you could, what you did was binary neutron star.
Yeah, so I only consider binary neutron star, but so Tanvir result can be more easily explained by the black hole neutron star binary because the mass of ejecta could be very high.
I thought you were saying that you'll be stuck if you use binary neutron star black hole.
No,
I thought it can be done even with binary black hole neutron stars. The Tanvir et al. Result can be explained. That's what he's saying. It's even more easy to explain.
But
What you are saying though is correct. Each parallel space is not degeneracy. The question is what we have.
And if you explain that with just one population, it's not necessarily that I would believe that this is the only solution you can get. And the more natural solution is mixture of all those things: supernovae, black hole neutron stars, and neutron stars. And then you start questioning your conclusions. So just to keep that in mind.
Yeah, true. Yeah.
Any other questions or comments? I just have one comment. So there was the early part of the talk was a part of the talk that has a robust. I keep repeating myself because the in-spiral is providing fairly model-independent constraint on the equation of state.
Yeah.
To use electromagnetics or nucleosynthesis to constrain the equation of state is going to be very hard, very challenging. But to address some of the points that Chris made, there is a part of the signal that is clean compared to all of this, that constrains the equation of state.
Okay.
So there are two pieces, and that relies on the detection of gravity waves.
That I take, yes. Yeah, that's understood.
Yeah. Yeah. Yeah.
If there are no further questions, let's thank Masaru again for
The 1.8, 1.8, right? They're certainly excited.
Very nice talk. A very minor point.
Oh yeah.
Just for clarification, when you were showing the animation of the electron fraction, I'm wondering if the legend on one of those was flipped.
Sorry, this is extremely heavy, so just a moment.
Okay.
Yeah, just a moment. This file has a 2 GB. Oh, something is wrong. Maybe memory. Yeah, this one.
That's the question. So the color coding. I mean here, this is 0.5, but if you look